Okay, today I'm going to be solving quadratic equations by square roots and also using factoring techniques. So in our warm-up, we're going to just practice simplifying the expression. Hopefully you learned in geometry that you cannot leave a radical in the denominator. If you see a radical in the denominator, we have to do something called rationalize. Okay, in order to rationalize expression, I'm going to multiply both the top and bottom by the radical that I see in the denominator. What happens then is I would get 6 radical 2 up top if I multiply the 6 times radical 2. And here if I multiply radical 2 times radical 2, I'd end up with radical 4. Now that's nice. When you multiply by the radical by itself, you can see that I get a perfect square under that root. So because 4 is a perfect square, I can simplify that. The square root of 4 would end up being 2 because 2 times 2 equals 4. Okay, or you can say that the square root of 4 equals 2 because 2 squared equals 4. Okay, so once I get that in reduced form, I can simplify this further. We always simplify outer parts with outer parts and numbers under the radical with other numbers that are under the radical. So this would end up reducing to 3 radical 2. For part 2, same thing. You can see we have a radical 3 in the denominator. So all I'm going to do is I'm going to multiply the top and the bottom by that square root of 3. I'm going to get 6 square root 3 up top. And on the bottom, when I multiply across, again, only like parts get multiplied. So the 5 and the 1 will get multiplied because those are both numbers outside the radical. So I get 5. And then we'll multiply the radical 3 by the radical 3 since those are both parts under the radical. So I'll get square root 9. Okay, and again, that's nice. When I multiply a radical by itself, I get a perfect square underneath that square root. The square root of 9 is going to end up being 3 because 3 times 3 is 9, or you could look at it like 3 squared is 9. Simplifying 5 times 3, we end up getting 15. Okay. Can I reduce this any further? Well, again, let's think about those outer parts. What are 6 and 15 both divisible by? 3. If I divide both terms by 3, I would end up with 2 root 3. And if I divide 15 by 3, I would get 5. So that's my reduced form. Okay, now that we've reviewed rationalizing, let's get into where it says solving quadratic equations. It says quadratic equation one variable is an equation that can be written in standard form with ax squared plus bx plus c equals 0. A root of an equation, we already talked about this last note. It's a solution of the equation. We can use the terms root, solution, 0, and x-intercept interchangeably. So don't forget about that. Quadratic equations can have none, 1, or 2 real solutions. And we can use 5 different techniques in order to get these solutions. We can solve quadratic equations by graphing and finding the x-intercepts, using square roots, factoring. You could also use quadratic formula or completing the square. Today, our main focus is going to be on using square roots and factoring. Okay, when you are using square roots, you want to write the equation in the form something squared equals a constant, where u could be an algebraic expression. And we're going to solve this by taking the square root on each side. When solving by factoring, you want to set the equation equal to 0 and then start factoring. Okay, so for solving quadratic equations using square roots, it says don't forget to rationalize the denominator. I'm going to start by identifying what expression is being squared. So if I look at this first example here, what is being squared? Is 4x being squared or just x? Well, it's just going to be x that's being squared. So that's what I want to try to get by itself. Okay, we're basically going to undo the order of operations to try to isolate x squared. So we're going to undo any addition or subtraction first, and then we'll undo any multiplication or division, kind of working backwards. So I'll start by adding 31 to both sides. So we get 4x squared. That becomes 0 when you add that. Here, 10, carry the 1, 4, 5, 6, 7, 8. Okay, divide both sides by 4. So we get x squared equals 20. When I square root both sides, we would get x equals plus or minus the square root of 20. Don't forget that plus or minus. It's so important. You'll be missing half of your solutions if you don't forget to do plus or minus whenever you take an even root. So I'm just going to write a note off here to the side. Even root. You need the plus or minus. So that's square roots, fourth roots, sixth roots. Okay, anytime you're taking an even root, you need plus or minus. Okay. Also, I don't want to just leave this as the square root of 20. 20 is divisible by a perfect square. Let's think about perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and you can see I went past 20. 20 lies somewhere in between here, and I need to determine what the largest perfect square is that 20 is divisible by. Is 20 divisible by 16? No. Is 20 divisible by 9? No. Is 20 divisible by 4? Yes. So I can break 20 down into 4 times what? 4 times 5 is 20. Okay. And really, then I have a perfect square that's being multiplied by something that's imperfect. And I can simplify the perfect part. Square root of 4 would be 2. So I get plus or minus 2 root 5. All right, let's head over here to part B. Part B, again, we're trying to isolate the quantity that's being squared. So in this case, x is being squared. Let's try to get it by itself. So I'll subtract 9 from both sides. We get 3x squared equals negative 9. Again, we're trying to get x squared by itself. So we're going to take this expression and divide by 3. Whatever I do to one side, have to do to the other side. So we get x squared equals negative 3. Then I'm going to go ahead and square root both sides. Don't forget, anytime I'm doing a square root on both sides, we need to put plus or minus. And so we get x equals plus or minus the square root of negative 3. This is a problem. I cannot have a negative number under a square root. This would be an example where there is no real solution. And let me explain why. So I want you to imagine just taking the square root of 4. Okay, the square root of 4, that's equal to 2. Okay, and the reason why it's 2 is because 2 times 2 equals 4. Okay, so let's try to take the square root of negative 4. What would that be equal to? Is it equal to maybe negative 2? I don't know. Negative 2 times negative 2, does that equal negative 4? No, it equals positive 4, so that does not work. It's also not going to be 2 because 2 times 2 is also positive 4, so that doesn't work. There's really no way to simplify the square root of a negative number. Okay, so in that case, we would have no real solution. Anytime there's a negative underneath an even root, you're going to have no real solution. All right, let's try part C. Now let's think again about what is being squared. In this case, x plus 3 is being squared. Okay, so we want to try to get that entire squared expression by itself. So how am I going to do that? Well, I could think about dividing both sides by 2/5. But really, rather than dividing by a fraction, instead I'm going to multiply by the reciprocal of that fraction. So I'm going to multiply this entire side by 5/2. Okay. And what's going to happen when I multiply by 5/2 is I'm going to get 10 over 10, which is just 1. Right? So really it gets rid of that coefficient, right? The 5's cancel, the 2's cancel. And on the left-hand side, I'm just going to be left with x plus 3 squared. Now, whatever I do to one side of the equation, I have to do to the other side as well. So I'm going to multiply by 5/2. 5 times 5 is 25. So we'll get 25 over 2. Okay. Let's go ahead and go from there to now that we've got the squared expression isolated, I can take the square root on both sides. So I get x plus 3 equals plus or minus the square root of 25 over 2. All right, and then I'll go ahead and finish getting x by itself by subtracting 3 from both sides. So So I'll have x equals negative 3 plus or minus the square root of 25 over 2. Now, I don't want to leave my radical expression looking like that. Really, I can simplify the square root of 25 pretty easy. That's just 5. But I cannot simplify the square root of 2. So I'm going to leave it just saying the square root of 2 for now. Okay. Again, I don't like that answer because we should not have a square root in the denominator. So what do I have to do? Well, in order to get the square root out of the denominator, I would have to rationalize the expression. So I'm going to multiply just the 5 over radical 2. I'm going to multiply the top and bottom by the square root of 2. Multiplying across, 5 times radical 2 is 5 radical 2. Here, multiplying across, radical 2 times radical 2 is going to be radical 4, which I like because square root of 4 can be reduced down to 2. Okay, so really let's rewrite this expression right here, 5 over radical 2, rather than putting that in my answer. I'm going to put plus or minus 5 root 2 over 2. Okay, and that's going to be my simplified answer. Okay. At this point, why don't you pause the video and try the following student practice problems on your own, 4, 5, and 6. Okay, welcome back. Let's go ahead and run through these quickly. We're trying to isolate the squared term, so I'll subtract 14 on both sides. We end up with 2/3 x squared equals 6. To get x squared by itself, we're going to multiply both sides by the reciprocal of 2/3, which is 3/2. Okay, 3's cancel, 2's cancel. So we end up getting x squared equals 6 times 3 is 18 divided by 2. So we get x squared equals 9. And when I square root both sides, don't forget your plus or minus. 9 is a perfect square. Remember, 3 squared is 9, or you can think about 3 times 3 is 9. So the square root of 9 is just going to be 3. Okay, and our answer is going to be plus or minus 3. Okay, let's try the next one. Again, we're trying to get the squared term by itself. So I'm going to start by subtracting 1 on both sides. We get negative 2x squared equals negative 7. Divide both sides by negative 2. We get x squared equals 7/2. Square root both sides. We get x equals plus or minus the square root of 7 over the square root of 2, which I cannot leave that as an answer because it's got a radical in the denominator. So I have to rationalize. Multiply top and bottom by the square root of 2. So we get x equals plus or minus the square root of 14 over, well, let's see, this would end up being the square root of 4, which reduces just to 2. Okay. I cannot divide 14 by 2 because 14 is under the radical and 2 is outside the radical. Okay, so we cannot divide those numbers. Numbers outside the radical can only be divided by other numbers outside the radical, and numbers under a radical can only be divided by other numbers under a square root. Okay, for this one we have to figure out what we're squaring. Here we're squaring x minus 4, so I have to isolate that quantity. Okay, so I'm going to start by dividing both sides by 2. We get x minus 4 squared equals negative 5 over 2. Square root both sides. We get x minus 4 equals plus or minus the square root of negative 5 over the square root of 2. And then here we would add 4 to both sides to get x by itself. So we get 4 equals plus or minus the square root of negative 5 over the square root of 2. Okay, now normally I'd rationalize this expression because I don't like to have I don't like to have a radical in the denominator. But in this case, I'm not even going to bother rationalizing. The reason why is because right here I see that we have a negative under a square root. You cannot have a negative under a square root and get a real solution. So right then and there, I'm going to stop simplifying and I'm going to put no real solution. I could have told you way up here, as soon as I saw that I was putting the square root around a negative number, we could have stopped at that point and put no real solution. All right, so we just got done going over solving quadratic equations using square roots. When we solve quadratic equations using square roots, don't forget to rationalize the denominator. We saw that here in this example where we got 5 over root 2, and we had to rationalize. We also saw that over here when we got radical 7 over radical 2, and we had to rationalize. Okay, so don't forget to simplify completely. Again, if you get a negative under that radical, you immediately write no real solution. Okay, it's just that we can't take the square root of a negative number. If that was a cube root or something, it would be okay. It's just whenever you're taking an even root of a negative number, there's no real solution. So here's the process we're going to go through. We're going to set the equation equal to 0, factor, then set each factor equal to 0 and solve. Okay. So it says the zero product property is why we refer to the solutions as zeros of the function, which is interesting. Okay, we're looking for one or both of the expressions could equal 0 if the product is equal to 0. All right, so let's take a look at this. Again, the first step is I want to get this set equal to 0. So I'm going to start by subtracting 45 on both sides. So I get x squared minus 4x minus 45 equals 0. Set up our parentheses. What times what is x squared? That's going to end up being x times x. Then what are two numbers that would multiply to give me negative 45, but add or sum to give me negative 4? 9 and 5. Because this middle sign is negative, the bigger number is going to have to be negative. And check. Your outers are 5x and your inners are negative 9x, and those would sum to a negative 4x in the middle. Okay, so that looks good. Once you have your expression factored, we're going to set each factor equal to 0 and solve it. Okay, we add 9 to both sides here. So we get x equals 9. And here we'll subtract 5 from both sides, and we get that x equal to negative 5. So those are both our solutions. If we want to write it as a solution set, we always want to put the lower number first in those fancy brackets, and then the bigger number second. So you could express your solution this way as well if you'd like. Another way that you could have factored this, if you wanted to use the x method, okay, is that we would put the AC on top. A is 1, C is negative 45. So if I multiply those, we get negative 45. We're going to put the B on the bottom. B, if I look at this, was negative 4. Okay, and then we put it over the leading coefficient, 1. Okay. And then I'm asking myself, what would multiply to give me 45, but sum to give me B? And that would be negative 9 and 5. Okay, and then we think about just kind of rotating this. So that's where we get the x minus 9 factor and the x plus 5 factor. Okay, in this example, it says find the zeros. What word or words would be a synonym for zeros? Zeros could be roots, solutions, or x-intercepts. Okay, and how do I find an x-intercept? What would I do to find an x-intercept? X-intercepts are found by plugging in 0 for y and solving for x. So if I plug in 0 for y, this would look like 0 equals 2x squared minus 11x plus 12. And I need to factor this to solve for x. Is there a GCF? It doesn't look like all of the terms are divisible by 2. So there's no GCF. Okay, so I'm going to set up my parentheses. What times what gives me 2x squared? That would be 2x times x. What times what would multiply to give me 12? There's a couple things. 1 and 12, 2 and 6, 3 and 4. What combination of those could get me to a negative 11 in the middle? Well, I might have to do some guess and check work here. I know I can't have anything that's divisible by 2 in that first blank because then there'd be a GCF. And I know from looking at the original equation that there was no GCF. So I can't use 2 or 6. I wouldn't want to put the 4 in that blank, but maybe we could put the 3 in that blank. Let's see what we have here. We have 8x and 3x. That could get me to 11, right? We want a negative 11, so they'd have to both be negative. So make this a 2x minus 3 and an x minus 4. Okay, and if I'm looking at this, just double check to make sure this would multiply out to give you your original trinomial. We would have 2x squared. This would be your minus 8x minus 3x, which would give you the negative 11x. And last times last would be positive 12. So that looks like that works. Okay, so if you want to use x method, you could AC. A times C would be 24. What's my B value? My B value was in the middle, negative 11. Okay, and we got to put these over A. A was 2. What would multiply to give me 24 and sum to give me negative 11? Well, what are some things that multiply to give me 24? We could have 6 times 4, 2 times 12, 8 times 3. I think 8 times 3 would work. We would just have to make this negative 8 and negative 3, right? Negative 8 times negative 3 would be 24. But when you add those numbers together, you would get negative 11. Okay, see if either of these reduce. Negative 8 over 2 does reduce. They're both divisible by 2, so we get negative 4 over 1. Whereas negative 3 halves does not reduce. So I'm just going to leave that as negative 3 halves. Okay, and then we turn this. So 1 becomes the leading coefficient for x. We get x minus 4. Turn this. 2 becomes the leading coefficient for x. So we get 2x minus 3. Those were our factors, x minus 4 and 2x minus 3. Okay, set each factor equal to 0 and solve. So here if I add 3 to both sides, I would end up with 2x equals 3. Divide by 2, we get x equals 3 halves. Here if I add 4 to both sides, we get x equals 4. Okay. If you want to write it as a solution set, a list of x values, we have to determine what's a smaller number. Okay, this is really 2 goes into 3 one time, and then we have a remainder of 1. So that's really 1.5. So that's going to be a number smaller than 4. So it will go first. All right. At this time, go ahead and pause the video and see if you can solve these equations by factoring. Welcome back. All right, we're going to solve these by factoring. This first one's already set equal to 0. So I'm going to set up my parentheses. First times first equals x squared. So that's going to be x and x. What number is going to multiply to give me 35, but sum to give me 12? What are some things that multiply to give me 35? I know 7 and 5. Does that add to give me 12? 7, 8, 9, 10, 11, 12. Yes, it does. So I'm going to use 7 and 5. These are all plus signs, so I'm going to make these have plus signs. Set each factor equal to 0 and solve. If I subtract 7 from both sides, we get that x is negative 7. Here, if we subtract 5 from both sides, we get that x is negative 5. Okay, if you want to write it as a solution set, it would look like this, where we would put negative 7 first, since it's the lower number, or the most negative number, and then negative 5 would come second. Okay, so you can write it either way. You can write it this way, or you can write it this way. This one is not set equal to 0 yet, so that's how I would have to start, is by setting it equal to 0. We'd get 3x squared minus 5x minus 2 equals 0. Doesn't look like there's a GCF, so I'm going to set up my parentheses. First times first has to give me 3x squared. So we have 3x times x. Last times last has to multiply to give me -2, where there's not a whole lot of options for that. The only things that would multiply to give me 2 are 2 and 1. And somehow you have to get a -5 in the middle. So let's just try it. If I put a 2 there and a 1 there, we'd have 3x and 2x. We could get to -5x using that. We just would have to make both of those negative. So let's see if that would work. My outers are -3x and my inners are -2x, and that would sum to give me -5x. And let's just check to make sure our first times first and last times last work. First times first would be 3x squared. That looks good. Last times last would be, see how last times last would be a +2, not a -2? So that is not going to work. All right, let's try something else. Let's flip it. Let's put the 1 there and the 2 there. This is going to be 6x and this is going to be 1x. Can I get to -5x? Yeah, I'd have to make the 6x negative, right? Because those would then sum to -5x. If that's the case, then this would have to be +1 and -2, right? Just try that out. See if it works that time. First times first is 3x squared. Outer times outers, -6x. Inner times inner is x. And last times last is -2. And this would combine in the middle to give me -5x. Okay, so that time that worked. Awesome. Now let's set each factor equal to 0 so we can solve. 3x plus 1 equals 0. X minus 2 equals 0. Here, if I subtract 1 from both sides, we get that 3x is equal to -1. Divide both sides by 3, and I would get -1/3. Here, if I add 2 to both sides, I could get that x is 2. Now, you can see that was a little bit harder to do guess and check with. If you wanted to use the x method on something like that, it might be a good strategy. Remember, AC goes up top, so 3 times -2 would be -6. B goes in the bottom. B was -5. Okay, then we've got to put each of these over A, which A was 3. All right, now ask yourself, what's going to multiply to give me -6, but sum or add to give me -5? That would be multiply to give me -6, but add to give me -5 would be -6 and 1, right? -6 times 1 is -6, and -6 plus 1 would be -5. We'll see if this reduces at all. This does. 6 and 3 are both divisible by 3, so I'd have -2 over 1 if I divide top and bottom by 3, and 1/3 does not reduce. Okay, so now I turn this. 1 becomes my leading coefficient for x, so I'd have 1x minus 2 as a factor, and over here, if I turn the wheel, we would get 3x plus 1 as a factor, and those were our two factors. Okay, so that's a more systematic approach. Down here, we're just doing more practice with finding the zeros of the function. Remember, what is a synonym for the word zeros? Solution, root, x-intercept, those are all synonyms. Remember, to find an x-intercept, all I do is I plug in 0 for y and solve for x. So if I plug in 0 for y here, I'd have 0 equals x squared minus 8x. It's already set equal to 0, so I'm going to use factoring to help me solve for x. What factoring technique could I use? I'm going to do GCF factoring. Both of them have what? An x. So if I divide out an x from each term, remember I subtract exponents. So x squared divided by x would be x to the first. When I take 2 minus 1, I get 1. Then we have minus. These x's would cancel and just give me 8. -8, right? Minus 8. Set each factor equal to 0 and solve. We get that x is 0. Here, if I add 8 to both sides, we would get that x is 8. Right, again, if you want to write it as a solution set, you could. Just make sure the lower number goes first. Over here again, I am just setting the equation equal to 0 in order to find the zeros of the function. Does this have a GCF? I don't think it does. 49 is, the factors are 1 and 49 and 7 and 7. And I know 4 is not divisible by 7 or 49. Okay, so let's factor this. There's a couple different options here. First times first has to be 4x squared. So you could use 2x and 2x, or you could use 4x and x. So we're going to have to think about that. Last times last, remember, has to give me 49, which we've already kind of talked about the factors of 49. It's either 1 and 49 or 7 and 7. I'm going to just try 7 and 7. Let's see where we're at, which one might work. Here, outers are 14x, inners are 14x. I think that works. That gets me to 28x. Whereas here, my outers would be what? Already, we're up to 28, right? And then 7. That's not going to work. All right, so I'm going to get rid of this second option because I don't think that one is going to work. This first option does seem to work, though, right? My outers are 14x and my inners are 14x, and those would sum to 28x. And because all of these are addition signs, I'm going to make these addition signs. Okay, now that we have it factored, let's set each factor equal to 0 and solve. We have 2x plus 7 equals 0, and again, 2x plus 7 equals 0. If I subtract 7 from both sides, we get that 2x is negative 7. Divide both sides by 2, we get negative 7 halves. And really, if I were to solve this, we would get negative 7 halves as well. You only have to write it once, though. Okay, just x equals negative 7 halves. If you're interested in enrichment, you can watch the enrichment videos to see how we can solve quadratic equations in the real world, or why we solve quadratic equations in the real world.